Hey, good morning everybody. This is Mr. Ainsworth, and we're going to get into a big review here covering at least 20-something problems over Chapter 8 here in Precalculus. And sit tight, plan on at least an hour here, and get ready. Get your calculator out, have that ready. Get your spiral out unless you want to print off the blank copy or the student copy here on my website. Or just open up that spiral, get your calculator out, fold it in half here, go in two-column format. Problem on the left and all the process solution on the right hand side, so you can use it as a study tool. As I pointed out here, okay, you can fold along the vertical line here and look at the problem side and use it as a study tool. Practice it again, because it's one thing doing them with me as I explain something here, and it's one thing doing them on your own, and it's another thing doing it easily and quickly so you can master these problems. So take really good notes. Follow me along here unless you want to work ahead, and then use this as a pause and play video. Pause it right now, go for it, and then play and check. And that of course can be done any time. So pause and play. In fact, let's write that down. Pause, alright, and play all through the video. Obviously try it first, pause it, try it, and then check it and play and watch me summarize it and check all your work. And if you don't use the video, well, that's cool too. You can always just look at my hard copy solutions, but always check your work. Okay, check everything, not some of it, but all of it. All right, so let's get right into it here. Let's take a look at this. I'm starting in section 8.5 here for the first 7 problems here. Just pulling out homework problems. This happens to be number 4 in your homework. Okay, and by the way, instructors do that a lot. I assign mostly odds, so you can check them in the back, and also check them with my solutions. But instructors pull out even problems all the time. So if I assign number 5, then you better be able to do number 6. If I assign number 13, you better be able to do number 14. Because typically in textbooks, the evens are associated with the odds. So when instructors hand select problems, and then just make sure you can do the other ones too, because usually they're test questions. So anyway, so let's practice here. Here we go. We're going to take 8 cosine squared x minus 3 equals 1, and we're going to isolate the function here, just like we do in Algebra 1 and 2. All right, I'm going to add 3 here, and I get 8 cosine squared x is equal to 4 divided by 8, and I get cosine squared x is equal to 1/2. I want to square root both sides, here and here, and I get cosine x now is equal to plus or minus 1 divided by rad 2, which is equal to plus or minus root 2 divided by 2. And as you guys know, if you look at the 45, 45, 90, this is rad 2 here, and this is rad 2. The cosine of 45 degrees is rad 2 over 2. And this is pi fourths in radians here. We want to get our answers in degrees here. The plus or minus indicates all 4 quadrants. Okay, right here. All 4 quadrants. Okay, you could separate this into 2 equations. Cosine x equals root 2 over 2, and then cosine x equals negative rad 2 over 2. The first equation will give you solutions in 1 and 4, and the second one in 2 and 3. But the simple way to do it is just understand that this plus or minus gives all 4 quadrants, using 45 degrees as your quadrant 1 reference angle. So our first solution here is 45 degrees. We're doing it in degrees here. That indicates right here that you're in degrees, as opposed to radians. If it was 2 pi, then it'd be in radians. And then I put pi fourths here. That's quadrant 1. Quadrant 2 is pi minus that. So 180. We're in degrees here. So 180 minus 45 is 135 degrees. And then to get from quadrant 1 to quadrant 3, just add 180. So 45 plus 180, well, that's 225. And then in quadrant 4, it's 360 minus 45, the quadrant 1 angle, and that's 315. Okay? And just remember this here too. Let me draw this. Go ahead and bisect all those. This is 45, 135, 225, and 315. All right? So you're looking at those angles right there on the 45, 45, 90. Quadrant 1, 2, 3, and 4. All right, you get 4 solutions here because of the positive negative. Okay, so 4 solutions. Next one, you get a quadratic. And typically when you have quadratics, which are second degree functions, you set equal to 0, and that's what we want to do, is you want to set equal to 0 first. Alright, and that's not too hard to do. We're going to take 2 tangent squared x, excuse me. We're going to subtract the 3 tangent x here. We're going to add the 1. We're going to set that equal to 0. And after you set it equal to 0 first, you want to factor it. Alright? Most of the times, they're factorable. And the books are designed that way. However, it's not always the case. Okay, so you put the factors of 2 tangent x first. Alright? 2 tangent x times tangent x gives you 2 tangent squared x. Factors 1 last, and then you just add signs. And I want a negative 3 in the middle. This gives me 1 tangent x. This gives me 2. I need a negative 3, so make them both negative. Check the last. Negative 1 times negative 1 is positive 1. Okay, so we're good to go. So we factor, and now we want to set each factor to 0 and solve. So set each factor equal to 0 and solve each. Okay, so I have to solve 2 tangent x minus 1 equals 0. And we have tangent x minus 1 equals 0. Solving the first one, we get tangent x equals a half, because we've got to add 1 divided by 2. The next one, I get tangent x equals 1. Okay, now, 1/2 does not exist on the special right triangle, so this is a calculator problem. So calc needed here. Because of the 1/2, it's not a one of those nice ratios. But we do know that tangent is positive in quadrants 1 and 3, so I need a quadrant 1 solution and a quadrant 3 solution. So I get my quadrant 1 first by taking the inverse tangent of a half, and that's going to be approximately equal to something. And then I'll add pi to it. Let me see, these got to be in, we're going to go in radians here, so 0 less than or equal to x less than 2 pi, so we'll be in radians here in a minute. So this is a calculator problem, so let me pause this and get my calculator here. Alright, I've got my calculator, and the first thing we want to do is check to see what mode it's in. And I notice I'm in radian mode. If the degrees were selected, I'd be in degree mode. But I want my answers in radian, so put in radian mode, go second mode to quit out. And now what I need to do is take the inverse tangent of 1/2, so, or 0.5, either one. And I get 0.464 radians. Okay? So I get 0.464 radians. That's my first solution. All I have to do is add pi to that to get my quadrant 3 solution. So my first one, x1, is this. My x2 is equal to pi plus 0.464. So all I have to do here is go add pi to it, and I get 3.605. So my second solution, 3.605 radians. Again, these are in radians. Those are my quadrants 1 and 3. Now my next one here is easy. You don't need a calculator. No calc needed here, because we know that the tangent of 45 degrees is 1. So my third solution here is pi fourths. Alright, and it's positive in quadrant 3 as well, so add pi to that, and you get 3 pi fourths. Okay, excuse me, add pi to that, I get 5 pi fourths. Alright, so no calc needed here. So be exact when possible. So be exact when possible, okay, when possible. Now I get 4 solutions. So where are they? This one, and these two here. I got 4 solutions here. Alright, that's number 2. Number 3, again, I'm just trying to pick different types here. I have tangent squared x is equal to tangent x, and what I'm going to do is get everything to one side. So I get tangent squared x minus tangent x equal to 0. And you might ask, why do that? Why do I set equal to 0? Well, that's typically how you solve quadratics. That's the reason why. I mean, last year you solved this in algebra 1 and 2, and we set it equal to 0. This is algebra 2 now, okay, or even algebra 1. We factored out the GCF, okay, and we got x equals 0 and 1. All right, we never divide out x here. We never divided x here. That eliminated solutions. You never divide by tangent, because that will eliminate solutions. So never, okay, divide, okay, out or cancel out, okay, a function. And I'm talking about a variable x too. Okay, never do that. Don't divide by tangent x here, don't divide by x here, because if you do, you eliminate solutions, and that's not good. Okay, just factor out the GCF. That's all you have to do. So tangent x times tangent x gives you the first term, and then minus 1. Distribute through, you can see what I'm talking about. So what did I do? I factor out the GCF, just common algebra technique. Now I set them both to 0. So when is tangent x equals 0? When is tangent x minus 1 equal to 0? And this is tangent x is equal to 0 when the sine is equal to 0. And that's at 0 and pi. Okay? And then when is this equal to 1? Well, we already discussed that. It's equal to 1 when x, the angle here, is pi fourths and 5 pi fourths in quadrants 1 and 3. Quadrant 1, quadrant 3. So I have 4 solutions: 0, pi, pi fourths, and 5 pi fourths. 4 solutions there. If you're hearing something in the background, that's my big Dane and my lab going crazy over there. Be careful, guys. Don't destroy the house. Okay, now here's a different one here. If you've seen a variation of this in my notes and also your homework. All right. So what I'm going to do here is try to rewrite this equation in terms of one function only. All right. And so what I'm going to do is just simply, I'm going to divide by cosine to create a tangent. That's what I'm going to do. So I'm going to divide everything by cosine. Now I know I said earlier that never divide out a function, and that is true. But I'm not dividing out or canceling out a function here. I'm transforming the equation. This becomes tangent. This becomes 1. This is still 0. So I didn't cancel out a function. I transformed it into a new function called tangent. And then, of course, you just isolate the function. All right? And you know the tangent of 45 degrees is 1, but this is negative now. So now we're looking at quadrants 2 and 4. So my reference angle is, pi fourths. Okay, that's quadrant 1. But we're looking for quadrants 2 and quadrant 4 here. So x equals pi minus pi fourths. This will give me my quadrant 2 angle, and I get 3 pi fourths. And then my second solution here would be 2 pi minus my reference angle, which would be 7 pi fourths. Okay, so I'm looking for quadrants 2 and 4 because, because it's negative right here. Okay? So I'm just trying to show you different types of equations here so you get some experience. Okay, so now let's see here, number 5. All right, let's see what happens here. Let's take this on the right-hand side and let's go for it. Okay, I have to try to rewrite in terms of one function only. So what I'm going to do is I know that any squared function is probably a Pythagorean identity. And I know, over here, I love saying that, I knew the following, that secant squared x is equal to 1 minus tangent squared x. And you guys might be saying, hey, wait a minute, that's not true, it's 1 plus, excuse me. Why is that? Well, just go back and look in your notes in the Pythagorean identities. This is one of them. So what I do is I substitute that in. So I get 2 times 1 plus tangent squared x plus tangent x, and I might as well just subtract the 5. All right. Why? Because we want to set it equal to 0. So distributing through, all right, you get 2 plus 2 tangent squared x plus tangent x minus 5 equals 0. It's a quadratic, and you need to simplify things here. So 2 tangent squared x plus tangent x. 2 minus 5 is a negative 3, and I get this. All right. So let's try to factor it here. So 2 tangent x times tangent x here gives you the first term. Factors of 3. Oops, that's not correct. Let's put 3 here and 1 here. This is 3 here, and that's 2. 3 minus 2 is 1. So we want to go minus plus. Okay. And that's factorable. So from here to here, you factor. Now, if you're weak at that, you better see me on the side, because last year you factored stuff like this all day long. This is what it looked like back in Algebra 2. Well, 1 and 2, right? So, in fact, this is the same thing. Just instead of x, we have tangent x. So, no big deal, right? Okay, and then you set it equal to 0 here. So, 2 tangent x plus 3 equals 0. And then tangent x equals 1, or minus 1 equals 0, which equals 1. So minus 1 equals 0. Let's do the easy one first. Tangent x equals 1. That's equal to pi fourths. And the 5 pi fourths, we already talked about that. And this one here, you got to subtract 3 and divide by 2. So tangent x equals negative 3 halves. This is a calculator problem right here. Why? Because, well, this negative 3 halves doesn't exist on a 30, 60, 90 or 45, 45, 90. Okay, so the question is, what are you going to do? So what we're going to do is this. All right, we are going to take the inverse tangent, and we're going to get two numbers in quadrants. We're going to get a quadrant 2 answer, and then we're going to get a quadrant 4 answer. So x equals the inverse tangent of negative 3 halves. And that'll give me a number here, so let's do that on a calculator. The inverse tangent of negative 3 halves. That's quadrant 4 right there. So what I'll tell you what I'm going to do is I'm going to need my quadrant 4 answer first. All I have to do, whoops, come on, I need my calculator here. I'll tell you what, all I have to do to get to quadrant 2 is add pi to that. Because we're in quadrant 4, if I add pi, that'll give me quadrant 2. Let's see, pi minus, yeah, because the reference angle here is positive 0.98. To get to quadrant 2, I just take pi minus 0.98. So I might as well just add pi at this point. So let's just go to quadrant 2 immediately. So, whoops. Whoops, that's not either. So plus my answer. No, plus pi. Come on, Ainsworth. Let me try that again. Inverse tangent. I screwed up on the notation there. Negative 3 halves. Okay, plus pi. There we go. Answer. There we go. That's quadrant 2. So 2.15. Let me see what's. There you go. So 2.159 rounded to the nearest thousandths. Let me get my number back. So I'm going to subtract pi to get my number back. Okay. Now what I want to do to get quadrant 4, I just add 2 pi to it, go coterminal. So plus 2 pi, and I get that angle right there, which is about 5.300. So 5.300, that's quadrant 4. So I have two answers, one in quadrant 2, one in quadrant 4. All right, knowing what I know about pi, I know this is less than 3.14, so it's got to be less than 180 here. These are in radians, you've got to remember. Just to interpret that. So I have 4 solutions, 2 here and 2 here. Good problem because it tests to see if you can use your calc, and it also tests to see if you know how to use your special right triangles. So right here, calc needed. Why? Because negative 3 halves is not a special right triangle ratio, okay, for tangent. Okay, next one. Ooh, this looks like a beauty. All right, let's see what we got going here. Number 6. All right. So cosecant squared x minus 2 cosecant x minus or equals to minus 4 sine x. I'm going to get everything equal to 0 here. So cosecant squared x minus 2 cosecant x. Let me see if I add 4. If I add 4 sine x, let me see, plus 4 sine x minus 2 equals 0. Okay, so what is all this equal to? This is going to be a challenging one here, guys. This is going to be fun. So I'll tell you what. These are right here. This is 1 over sine squared x minus 2 divided by sine x plus 4 sine x minus 2 equals 0. Let's multiply everything through by sine squared x to clear the fraction. So from here to here, I'm going to multiply by sine squared x to clear fractions. This is one of those algebra 1 and 2 techniques as well. Alright, so here we go. I get 1 here minus 2 sine x here plus 4 sine cubed x minus 2 sine squared x equals 0. And now, well, I got to get everything. I'm going to get everything. Now I'm just going to rearrange terms. So rearrange 4 sine cubed x minus 2 sine squared x minus 2 sine x plus 1 equals 0. So rearrange. Okay, so, oh, this is incorrect here, so let me fix that. It's 4 sine cubed. Okay, so we're in descending order here, third degree, second degree. One of the, oh, this is missing something here. I think I made a mistake somewhere. Where did I make it? Let's take a look. Trying to find my mistake if I made one here. Let me see. Let me factor out a 2 sine squared. Let's see what happens. 2. I'm going to try factor by grouping here. Let me see if it works. Let me pause the video here. Okay, one of the factoring techniques that you learned in Algebra 1 and 2 is factor by grouping. So hopefully you know what that means. I'm going to give it a shot. Here's my first group and here's my second group. So I want to factor out a 2 sine squared x here. So 2 sine squared x times 2 sine x. 2 times 2 is 4, obviously. Sine squared times sine gives sine cubed. This gets all factored out, so minus 1. And I want to generate a 2 sine x minus 1 over here, and I can do that by distributing out a negative. So minus 2 sine x minus 1. I distribute out a negative. Got to change the sign there. Equals 1. Now what I want to do is factor the common factor out. So let's do that. So 2 sine x minus 1 times the leftovers. What's the leftovers? 2 sine squared x minus 1 is an invisible 1 here. Alright, so times 2 sine squared x minus 1 equals 0. Cool. And now we just solve here. So we have 2 sine x minus 1 equals 0. 2 sine squared x minus 1 equals 0. This one yields sine x equals a half. And in radians, 30, 60, 90, 2, 1 rad 3. The sine of 30 degrees equals a half. So that's pi 6. So we have x equals pi 6. And in quadrant 2, it's pi minus that. So 5 pi 6. So we have two answers there. And then here we have sine squared x is equal to a half after you add 1 divided by 2. Then sine x equals plus or minus 1 divided by root 2, which is equal to plus or minus rad 2 divided by 2, which means all 4 quadrants here. So all 4 quadrants, just like I was talking about earlier, so 4 solutions there. So here you're on the 45, 45, 90, so your first solution is pi fourths. Next one, 3 pi fourths. In quadrant 2, quadrant 3, 5 pi fourths. If you know the unit circle, you know these angles. And then 7 pi fourths for the fourth one. So we have 6 solutions here. How cool is that? 6 solutions. This is a cool problem because it takes factor by grouping. It takes zero product rule. You name it, it takes it. Alright? What an awesome problem. If you can do that, man, you're good. Alright, now we got sine x equals x divided by 2. Alright, so sin x equals x half. Let this one y1, this one be y2. So y1 equals sin x. y2 equals x divided by 2. We're going to intersect them and find the solution. Okay, intersect them and find solution. So let's go ahead and do that. Alright, let's go to y equals here. Turn these babies off, meaning clear them out. Let's enter in the sine function. Make sure you're in radian mode when you do this. And then go down here and write down x divided by 2. We're looking between 0 and 2 pi, so hit window. 0 to 2 pi, 0, this is 2 pi here. Go to graph. Okay. And let me see. Let's take a look at something here. Let's zoom in here. Trace. Let's go over here a little bit. Oh, no wonder. I didn't put the right function in. I was wondering what was going on. Okay, x divided by 2. That is going to look better. Let me go back here. So we have a solution here at the origin, and we have a solution here. So two solutions I'm looking for. So x equals 0 makes sense because sin of 0 is 0 and 0 divided by 2 is 0. So 0 is obviously a solution. But what is the other one? What is this one right here? So all you do is go second calc, hit number 5, go enter, enter, and put your cursor next to the intersection point here. Got to find your cursor though. Let me see, 1, 2. I'm going to enter in 2. So trace 2, enter, right about there. That's good enough. So go second trace, number 5, enter, enter. We're close enough. There we go, about 1.895. So that's good enough. So 1.895 radians. Okay? Those are the values. Those are the intersections. Okay, there you go. And that's how you solve it on the calculator. Pretty simple, as long as you can use a calculator. All right, next one. We're going to jump into section 4 here. We're going to do some proofs. 8 through 16 is on section 4. So as you guys know from class, you need to start off with the left-hand side, typically. So you're going to start off with sin x divided by sin x plus cosine x. Sometimes that's tough. So what I tell my students is to work backwards, 1 plus tangent x. Okay, and I work backwards here, meet in the middle, and then I work forwards here. So work forwards a little bit until you get stuck. Alright, and then when you get stuck, work backwards. And then you should be able to meet in the middle, and the proof is complete. And the question is, what do you do with this to get to this? So, work backwards. Okay, what's tangent? Well, tangent is sine x divided by cosine x. 1 plus the same thing, sine x divided by cosine x. Okay, it's maybe not too clear how to get to this point. So, let's compare sine x and then sine x divided by cosine x. Well, maybe we should just divide all terms here by cosine x and see what happens. So let's try that. Let's divide all terms by cosine x. So let's do that here. Let's do that to all three terms here. This one, and this one too as well. Cosine x divided by itself. And simplify. So let's work down here. So what does that give us? It gives us sine x in the numerator divided by cosine x, all divided by this plus this. So sine x divided by cosine x, with cosine, plus 1. Okay, that is nothing more than 1. Whoa. So this and this are the same. So the question is this the same as this? And the answer is yes, because these two things are equal. Alright, and these two things are equal. And the proof is complete, because the order in addition doesn't matter. So sin x divided by cosine x plus 1 is the same thing as 1 plus sin x over cosine x. Alright, so you start off with the left side. That first is equal to the second, equal to the third, equal to the fourth, equal to the fifth. So the first is equal to the fifth by transitivity, and the proof is complete. Okay, I started off on the left side, ended up on the right side. They're all equal, so the first must be equal to the last. There you go. Oh yeah, QED, quod eris demonstratum. Alright, that which was to be demonstrated. Alright, let's try it again. Start off with the left-hand side. So tangent x plus cotangent x, alright, divided by secant squared x. And my goal is to simplify it to cotangent x. So we need to work forward. Alright, so many different ways you can do this. Maybe we should go in terms of sine and cosine. Let's try that technique. So sine x divided by cosine x, that's the tangent here, plus cosine x divided by sine x, that is the cotangent, all divided by 1 divided by cosine squared x. As I told you guys, we need to combine fractions here. Always combine fractions, that is, in the numerator. Alright, so we do the three product rule right there. So sine squared here. So sine squared x plus cosine squared x divided by the product of the two, sine times cosine, all divided by 1 divided by cosine squared x. Now here the numerator is 1. So I get 1 divided by this right here, this denominator, which is cosine x times sine x, times the reciprocal, which is just cosine squared x. Multiply by the reciprocal there. So multiply by the reciprocal. Alright, then cancel. Alright, so this one gets canceled out with one of these, leaving a cosine up top, which is cosine x divided by sine x. Alright, and that gives you cotangent. Okay, so it's going to take some practice, but there you go. Alright, let's try it again. Moving right along, this takes a while. So how do you get from this to this? I mean from left to right. So cotangent theta now divided by sine of, not theta, but 90 minus theta. 90 minus theta. You know, why is that equal to cosine theta? Well, I don't know. Let's figure this out. We do know our identities here, that in our cofunction identity is dealing with complement. So sine of 90 minus theta is the same thing as cosine theta. Okay, they're equal. Take a look at your identities. So then you say, okay, cotangent is cosine theta divided by sine theta times the reciprocal of cosine, so times 1 over cosine theta. That gives you 1 over sine theta, which gives you cosecant. Alright, and the proof is complete. So pretty simple. Okay, number 11, we want to prove that cotangent x plus tangent x divided by cosecant squared x is equal to, oh well, it's equal to a whopping tangent here. So same thing, let's go ahead and rewrite. So cosine x divided by sine x, alright, that's this right here, plus tangent, which is sine x divided by cosine x, all divided by 1 divided by sine squared x. This kind of looks like the last problem, doesn't it? So go ahead and use the three product rule here. So cosine squared x plus sine squared x, all divided by the product of the two denominators. Divide that by 1 divided by sine squared x. This numerator is 1 here, so we get 1 divided by this, which is cosine x times sine x, times the reciprocal of this, which is just sine squared x here. Simplify a little bit. Okay, what do I get? I get, need some more room here. I get sine divided by cosine, so sine x divided by cosine x, alright, and that's equal to tangent x. Alright, there you go. Okay, now let's do some simplifications here, just straight simplify. So 1 divided by cosine x plus 1 divided by sine x, all divided by 1 plus sine x divided by cosine x. Alright, and we need to simplify this expression. So we're going to combine here. So combine this one here. I get sine x plus cosine x divided by cosine x times sine x. That's the numerator here. Okay, just the 3 product rule, 1, 2, and the 3. And then here, divided by 1, which is cosine x over cosine x divided by cosine x, plus sine x divided by cosine x. What will that give us? Well, it'd be sine x plus cosine x. I'm looking up here in the numerator. Divided by this cosine x times sine x. That's my numerator. All divided by cosine x plus sine x, cosine x plus sine x, divided by my LCD, which is just cosine x. And now that you have a fraction, you multiply by the reciprocal. So you have sine x plus cosine x, looking at my top fraction here, divided by the product of the two, times the reciprocal, which is cosine x divided by the sum, cosine x plus sine x. So check it out. All of this cancels out to 1. This one and this one cancels to 1, giving you 1 divided by sine x, which is cosecant x. Done. QED. Alright? Cosecant x. There you go. Alright. Let's continue here. We want to simplify this. So we know that cosine of 90 minus x, or theta, is the same thing as sine theta. Alright, you get cosecant theta. Done. Next one. You get cosecant squared x times sine squared x. This is 1 over sine squared x here, times sine squared x. That equals 1. Here we have cosine theta times 1 over cosine theta minus cosine theta. Distributing through, we get cosine over cosine, which is 1, minus cosine times cosine, cosine squared theta. That's equal to sine squared theta. Done. And here this is full, so secant squared here. So secant squared theta plus secant, I'm not thetas, I'm x's right here. Can't switch the variables. So secant times tangent, okay, plus minus secant, tangent times secant, that's the same thing as secant times tangent. So I'm going to write it like that so you can see that they look the same, and then minus tangent squared. There's your FOIL. Those cancel out. So I get secant squared x minus tangent squared x. And you might be thinking you're done, but you got to remember that secant squared x, we know that 1 plus, this is something we already know here, 1 plus tangent squared x equals secant squared x. So I'm going to do a substitution here. Okay, so I make the substitution and then simplify, and the tangent squareds cancel out and they get 1. Now I'm done. Okay, so let's just keep on going here, and let's rewrite cotangent as cosine theta divided by sine theta plus cosine theta, all divided by 2 times cotangent theta here. Okay, there's an identity there. They're cofunctions. Let's simplify right here. That gives you 1 there. And that equals cosine plus cosine. So that's 2 cosine theta divided by 2 cotangent theta. These cancel out, giving you cosine theta divided by cosine theta divided by sine theta. Okay, just rewrite there. Multiply by the reciprocal, I get cosine theta times sine theta divided by cosine theta. That's multiplied by the reciprocal. Alright, these cancel out, giving you just sine theta. Done. Okay? This is pretty cool stuff. Alright? Then, this one here, you get 1 divided by cosine theta plus, you know what, I'm just going to rewrite this actually, and I'm going to show you something. I need to combine fractions here. So you know what, I'm just going to go do it the old-fashioned way. I'm going to multiply by cosine theta times cosine theta because I can. This is just 1 here, so I can combine fractions. Use common denominators. Okay, and then what do I get? I get 1 divided by, this is cosine squared theta plus the sine squared theta, all divided by my LCD right here, which is just cosine theta. That's 1, so I get 1 divided by cosine theta, which is just cosine theta, after multiplying by the reciprocal. So this really tests you on your ability to work with fractions using a lot of basics. These next few problems here are in section 2, 1728. Get out your calc. Well, actually, the first few don't use the calc there. We're going to solve them in radians here. So radians. Why? Because, okay, we want less than 2 pi here. Okay, so 2 sine x equals 1 gives you sine x equals 1/2. That's positive, and sine's positive in quadrants 1 and 2. So quadrant 1 and 2. X equals the inverse sine of 1/2. All right, which is, well, if you can't visualize this in your head yet, you should be getting there. But we know that the sine of 30 degrees gives you 1/2. Okay, so TOA. All right, sine is opposite divided by hypotenuse. So opposite of 30 is 1, hypotenuse 2. So 1/2, which is also pi 6. Let's put pi 6 here and pi thirds here. So this gives you pi 6. Quadrant 2 is pi minus pi 6, which gives you 5 pi 6. Okay? So when the angle, or when b is 1 here, and the angle is not multiplied by anything other than 1, like it is here and here, you just get 2 solutions. But when b is not 1, you get either more or less solutions. Now here, b is 2. Alright, that means the period is 2 pi divided by 2, or pi, which means it's contracted. And whenever it's contracted, or shorter, okay, that means that it oscillates twice. Okay, from 0 to 2 pi, that is. And if it oscillates twice, going up, down, then up, down, excuse me, down and back, well, let me just draw a little sketch. It goes like this, but that's one period, and then another period, it does it twice. This is pi, and this is 2 pi. And that horizontal line at a half will intersect it at 1, 2, 3, 4 times. I'm looking for 4 solutions here, and the easy way to get that is just take b and multiply it by 2, which is the typical number of solutions like in part A. b is 2, you get 2 times 2 solutions, or 4 solutions. When b is 3, 3 times 2 is 6 solutions. When b is 4, you get 8 solutions, and so on. Alright, so let's solve this baby. And let's get these 4 solutions. So you isolate your function as you normally do. But this time you get 2x is equal to the inverse sine of 1/2. Alright, so 2x is equal to your pi 6 and 5 pi 6. Alright, plus multiples of the period for sine, which is 2 and pi. And that tells me that I get x is equal to, from here to here, I got to multiply by 1/2. So I get pi 12ths and 5 pi 12ths plus 1/2 of that, which is just n pi. And notice this right here, this is called multiples of the period. Multiples of the period. That's what this is right here. Period's pi. That's what this is. And if you want more solutions, simply add pi. So if I need another solution, go ahead and add pi here and add pi here to get another one. And pi is the same thing as 12 twelfths. It's common denominators here. So pi equals 12 twelfths pi here. So I simply have to add 12 in the numerator. So 1 and 12 is 13. So I get 13 pi 12ths here. Add 12 to 5, you get 17 pi 12ths here for 4 solutions. Okay? 4 solutions total. Here they are. 4 solutions in all. Now sometimes things change here. So b is 1/2. And b is 1/2, you get period is equal to 2 pi divided by half, which gives you 4 pi. So it's expanded. Opposite of contracted, it got longer. So it's stretched out basically. So what happens here? Well, let's go ahead and take a look at it. So we have 2 sine of 1/2 x here equals a half. No, not equals a half. I don't want that. I want it equal to 1. So change this to 1 here. Change this to 1 here too. Alright, so I get sine of 1/2 x is equal to 1/2 after you divide by 2. And that means 1/2 x equals the inverse sine of a half. Okay, well, that gives me 1/2 x equals pi 6, like I got before, and 5 pi 6, plus multiples of the period, 2m pi. It's always 2m pi for sine or cosine. And then to get from here to here, I just simply multiply by 2 to get my value of the variable. So I got to double everything. So this becomes pi thirds, because 2 times pi divided by 6 is pi thirds. And this is 5 pi thirds, because you get 10/6 or 5 thirds, plus 4n pi. And again, that corresponds to this. This is called multiples of the period. Multiples of the period. And this is how I get a lot of solutions. Alright? Now if I add 4 pi to either one of these, I'm beyond 2 pi. So I only have 2 solutions here because the period's expanded. Okay, so if I try to get them here, if I add 4 pi here, that'd be 12 thirds, so it'd be 13 pi thirds. This one would be 17, 17 pi thirds. This right here, these are beyond, greater than 2 pi, okay? So not a solution less than 2 pi. So that's basically what I'm saying. Not a solution less than 2 pi. So we don't count them. We just count the ones that are less than 2 pi. So we only have 2 solutions there. Alright, so I'm trying to show you all the different variations here. That's what I'm trying to show you. Now I'm going to switch from sine to cosine. Alright, so let's go ahead and give that a shot. So we have 2 cosine x equals root 3. That means I got cosine x equals root 3 divided by 2. Cosine is positive 1 and 4, so we have a quadrant 1 solution, quadrant 4 solution. X is equal to 2, 1 rad 3. So cosine of 30 degrees, or pi 6, is equal to root 3 over 2. So it's pi 6 here. And this is 2 pi minus pi 6, or 11 pi 6 for this one here. 2 solutions only, because b here is equal to 1. Alright, when b is equal to 2, the period is 2 pi divided by 2, or pi, so it's contracted. We have 4 solutions here. Alright, so I can tell looking there is that I have 4 solutions total. 2 times 2 is 4. 2 times 2 equals 4. Alright, so let's find them. So I've got 2 cosine of 2x is equal to rad 3. That means I've got cosine of 2x equal to root 3 divided by 2. So now I have 2x is equal to pi 6 and 11 pi 6. Just as I did before here, plus multiples of the period. Okay, so how do I get them? I got to divide by 2, or multiply by half. So I get pi 12 and 11 pi 12 plus n pi, the period. This is the period now, pi. So if I want some more solutions, I just add 12 12 pi. We know that pi equals 12 12 pi. We know that. We get common denominators here. So to get another solution, I add pi, and I get 13 pi 12, and I have to add pi in this one here. 11 and 12 is 22, so 23. So I get 23 pi 12. If I do it again, I'm out of the domain, so I'm going to stop here. Because I know that 24/12 is 2, so I'm under 2 pi here. So I have 4 solutions here. But here they are. 4 solutions. Alright, now let's handle this one. We've got 2 cosine of x divided by 2 equals root 3. Okay, isolate your function. Okay, solve for the variable by taking the inverse cosine now. So inverse cosine of rad 3 over 2. So x divided by 2 equals pi 6 again, and 11 pi 6 in quadrant 4. Multiply everything by 2 because I got to solve for x here, so times 2. And I get pi thirds here and 11 pi thirds here. Now 11 pi thirds is out of the plus, let me see, plus multiples of the period. So plus 2n pi and then plus 4 pi here. So 4n pi actually. Okay, and notice that 11 pi thirds is greater than 2 pi, so we're going to exclude this one because it's greater than 2 pi, and I only have one solution. One solution right here. That was a good one. Alright. So you can see the difference in how B affects things, you know, when you change it. Okay, now this one's a good example of when a calculator is needed. So here you have 4 sine of 4x equals 1. That means that sine of 4x is equal to 1/4, and this is not on the special right triangles. So this is calc required. Okay, so 4x here is equal to the inverse sine of 1/4, which means 4x is equal to, let's take the inverse sine now of 1/4, and let's do it in radians. So it's 0.256, I think. Let me see, 0.253. So let me see here, 0.253. That's quadrant 1. Now quadrant 2 is pi minus that. So pi minus 0.253 gives me my quadrant 2 answer. So let me get that. Pi minus my answer, I get 2.889. So 2.889 radians, that's my quadrant 2, plus 2n pi multiples of period. Then I divide everything by 4, because I got to solve for the unknown. Alright, and simplify, so I get x is equal to, might as well just choose this one here first because it's on my calculator, so divided by 4 equals 0.722. This is pi halves, so n pi halves. Notice that's my period there. This is multiples of the period again, which should make sense because right here B is 4, that means P is 2 pi divided by 4, or pi halves. So that's how we get more solutions there. Then I've got to add this pi halves repeatedly here. And I might as well just work on this one here. Might as well just add pi halves now and then add pi halves again. I'm looking for, let me see, B is 4, I'm looking for 8 solutions. So, and then another one, add pi halves. So let's do that. So add pi divided by 2, enter, 2.293, plus pi divided by 2 again. I get that one. So 2.293, 2.293, let me write that a little bit better. 2.293, have to add pi halves again, which is right here, so 3.864. So 3.864, add pi halves again. Plus pi divided by 2, 5.435. 5.435. That's getting close to 2 pi, or 6.28, so I'm not going to have any more after that. So I just keep adding multiples of the period. Now I have to do the same thing up here with 0.253. So I need that decimal back. Okay, so I need to take sine inverse of 1/4 again. So let me clear this out. Sine inverse of 1/4. Okay, now I need to divide it by 4. Alright, and that's my first solution. So 0.063. So 0.063 radians. Now I have to keep on adding pi halves. So add pi halves here, and then do it again. Okay, and then do it again. So add pi halves again. So plus pi divided by 2 plus pi divided by 2. So 1.613, so 1.63, I think it's 3, let's see. Actually 4, okay, and then 3.205. 3.205, this one's a 4. Add again, add pi, divided by 2, 4.776, so 4.776. So I get 8 solutions, okay, 8 solutions, right here. Alright, so, and then you can check them on the graph, okay? You can let this be y1 here, and this one be y2, and check them, see how many times this horizontal line at 1/4 intersects this graph, and it better be 8 times. Alright, that was a big daddy problem. Number 20. Almost done here, guys. We have to graph. Alright, so let's check this out. Y equals sine of 2x. Here, b is 2. So the period is 2 pi divided by 2, or pi. So I'm going to go out 1, 2, 3, 4, and call that pi. Amplitude is 1, so a is 1. So here's -1, here's 1. And when I graph the function, I graph my 5 points. Curve it out. Okay, 1 period only. 1 period only. Okay, the next one is 3, b equals 1/3. That means p is equal to 2 pi divided by 1/3, or 6 pi. So let's see here, let's go out 6 pi. 1, 2, 3, 4. That's 6 pi now. Amplitude is 3, so 3 here, -3 here. And then go ahead and graph. So here, here, here. Oop, down here. No. Okay, let's erase that 1 point. Alright, there you go. Make sure you label the axes. Label axes. Okay, this is 3 pi here. You can check to see if I'm right, by the way. 3 pi divided by 3 is pi. Sine of pi is 0. 0 times 3 is 0, so you're right there. Okay, that's how you can check. You can just check 1 or 2 points. You got it. Ooh, this is reflection. Okay, it's a reflection. So here we go. Amplitude is 2, so amplitude is the absolute value of -2, which is 2. So here's 2, here's -2. Period is pi, 2 pi, so period 2 pi, because b is 1. B equals 1 here. So go 1, 2, 3, 4, put 2 pi here. Now instead of going up and back down, we got to reverse that. So here, 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 and here. Curve it out. And check. Okay? This is pi, and this is pi halves. If I substitute pi halves in, I get sine of pi halves is 1 times -2 is 2. So pi halves comma -2. You can check that point right there. Check points. Check points, and then plot. Okay, next one, another reflection, but now b is 1/4. That means p is equal to 2 pi divided by 1/4, or 8 pi. Right here, a is equal to the absolute value of -2 again. A is 2. So here's 2, negative 2, 1, 2, 3, 4, 8 pi. Let's graph. So here, 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 and here. There you go. Okay, and this is 4 pi here. You can check 4 pi. 4 pi divided by 4 is pi. Sine of pi is 0. 0 times negative 2 is 0, and you're here. Okay, you can check any angle you want. Okay, let's switch it. Let's deal with cosine. Okay, so cosine, A is 3, B equals 1. Alright, so here we go. Gotta go up to 3, down to negative 3, 1, 2, 3, 4, put down 2 pi. Period is 2 pi, because B is 1. And we gotta go, cosine starts at the origin. So, excuse me, at the where the amplitude is. So 0, if you plug in 0, you get cosine of 0 is 1, times 3 is 3. So it starts here. You go here, here, here. Curve it out. Plot your points. Okay? Now here, B is equal to 1/3. That means P is equal to 6 pi. A is 2. Alright, so A is 2. That's negative 2. 1, 2, 3, 4. 6 pi. It's positive. So here, 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 here. Go ahead and curve it out again. Clean it up a little bit. Use your eraser. There we go. Alright, label axes. Make sure you label both axes. Okay? Here you have a reflection again. Okay? Here B is 2. That means P is equal to 2 pi divided by 2, or pi. So 1, 2, 3, 4. Place pi there. And then amplitude is 2. Negative 2, positive 2. But now you're starting here. Okay, there you go. You can check that too, by the way. You can take pi halves here and see if you get 2. 2 times pi halves is pi, times, or cosine of pi is negative 1, times negative 2, positive 2, and you get up 2 right here. So you can check points. Check points to verify graph. Okay, to verify graph. Not that hard. Alright, next one, 22. Do a little translating here. Okay, on this one, okay, A, B, H, K. So amplitude is 2. Shift for cosine is negative 2. Shift is negative 2 comma 1. Wave axis is 1. So the very first thing I'm going to do is let's see here, and B is pi thirds, so P is equal to 2 pi divided by pi thirds, and that's 6, period 6. So let's see here. So hang on for a second, let me clean this up here. Okay, so I first draw my wave axis. So y equals 1, wave axis. I have amplitude of 2, so I go up 2, down 2, and the wave's got to be between these lines right here. So here's my amplitude. Here's my amplitude here. Okay, now cosine usually starts at 0, 2. If it's not translated, it typically starts here. But it's been translated 2 left and 1 up. So go 2 left, 1 up. Now it starts here. I went left 2, up 1. Left 2, up 1. This is where I start. Okay? Then I go over 6 units to the right. 1, 2, 3, 4, 5, 6. This is where I end. And I have to divide that up into 6 equals, or 4 equal parts. Okay, so let me see here. So let me see, 6 divided by 4 equals 3 divided by 2 equals 1.5. So 1.5, so there's a 1.5 here. There's 3, 1.5, and then there we go. So divide up the interval into fourths. So let's see, I start here, then go to the wave axis, and then go over, and then down to a minimum, back up to the wave axis, and then end it. So no. Here. Okay, there you go. That's one period only. Okay, this one here, sine. This is a little bit easier here. So A, B, H, K. Shift is 1 comma negative 2. So 1 comma negative 2. Period length is 2 pi divided by pi fourths, or 8. Amplitude 3. So, and the wave axis, y is equal to negative 2. So I'm going to start off with the wave axis at negative 2. Okay, y equals negative 2. Amplitude of 3, so 3. Here's my amplitude, down 3. And it oscillates in there. Now sine would normally start at the origin, but it's been shifted 1 right, 2 down. 1 right, down 2 from the origin. So 1 right, down 2. So now I start here. Okay, start right there. Count 8 to the right, periods 8. Alright, 2, 4, 6, 8. And there. And then draw your function. To a max, back to the wave axis, to a minimum, here, and then you draw. Okay, one period only. Okay, next few problems. And I'm done because I am very tired. It is almost midnight tonight, and I'm doing it for you guys. I hope you understand that. All right, love you guys, man. That's why I do what I do. All right, try to help you out. We're going to try to write these in terms of sine and cosine. So the very first thing we need to do is draw the wave axis. Okay, 1, 2, 3, 4. 1, a minimum. This is minimum at 2, maximum at 4. The wave axis runs right through the middle of 2 and 4, which is right at 3. So the wave axis is here. Alright, wave axis, and that's y equals 3. I just average 2 and 4. 2 plus 4 divided by 2. 2 plus 4 divided by 2 is 6 divided by 2, or 3. So there's my wave axis. The shift, okay, for sine. Well, let me see. No, I got to get a period here. The period, let me see. I start at 0, end at 2, 2, 4, 6, and then 8. Period length. Alright, period is 8. B is equal to 2 pi divided by P, or 2 pi divided by 8, or pi fourths. Okay, so for sine, my shift, sine shift, would be simply straight up to the wave axis. So 0, 3. Alright, so I get y minus 3 equals amplitude, amplitude right here, a equals 1. So sine, 1 sine, was just sine, of my pi fourths times x minus 0. My cosine shift, okay, cosine shift would be to a max, starting at an amplitude of, let's say, starting here. So normally cosine would start here. So how do you get from here at 1, because it has an amplitude of 1, to a max up here? I got to go right and then up, right 2 and up 3. So my cosine shift is 2 comma 3. I get y minus 3 equals cosine, 1 is the amplitude, cosine of pi fourths times x minus 2. There we go. And that's problem number, well, it's 23A, but it's a homework problem actually. Okay, and my on this one here, I want to analyze the period, so I'm going to go start here, finish here. My period length is right here, and that's 7 pi 6 minus pi 6, right minus left, equals just pi, so my period is pi. That means that b is equal to 2 pi divided by the period, which is pi, or just 2. So b is 2 in this case. Okay, now I need to get some shifts. So my sine shift here. Let's work on that one first. Alright. Oh, my wave axis, it runs right through the middle of the wave, so it's the x-axis in this case. Why is that? Well, it went 3 to negative 3, and then 3 plus negative 3 is divided by 2. Well, that's 0, so y equals 0. The wave axis, y equals 0, it happens to be the x-axis. Okay, you can see that by inspection, but you can calculate it by averaging. The amplitude is 3 here, so my amplitude right here, a equals 3. Alright, now I need to start. So my sine shift, all I have to do is get to this starting point, so I just go right pi 6. Alright, that's all I have to do. I don't have to go up or down. So my sine shift is right pi 6, so it's pi 6 comma 0. So y minus 0 equals amplitude of 3 times the sine of pi, now, excuse me, 2, b is 2, 2 times quantity x minus pi 6. Okay, you don't need the 0 there, you can just put a y there. My cosine shift is going to be a little bit different, so let's go ahead and take a look at cosine shift now. How do I get to a max? Now this amplitude is 3, so how do you get from here to here? And all you have to do is move right. But move right how much? That's the big question. So let's figure this out. We need to figure this out. Okay, how do we do that? Okay. Sorry. Okay, so we have to figure out, where is this max, how far to the right. So I do know this, is that for a sine curve here, we take the period and we divide it up into 4 equal parts. So here's 2 equal parts, and then here's 4 equal parts. So we know the period length is 4, so this distance right here must be 1/4 of pi, or pi fourths. So all we have to do is add pi 6 to pi fourths, and we figure out how far we move to the right for the cosine shift. So right here, let's just calculate that. Pi fourths plus the pi 6, and that's common denominator is 12, so 3 pi 12 plus 2 pi 12 equals 5 pi 12. So right here, that is 5 pi 12, right up here to get to the maximum. So to get from here to here, okay, I got to go over 5/12 of a pi. So my cosine shift is 5/12 pi comma 0. So 5 pi 12 comma 0. So I get y minus 0 equals the amplitude 3 times cosine of b, which is 2, times x minus 5/12 pi. There we go. So, a little bit challenging, but that's how it's done. Alright, you guys? And I'm tired. It's almost midnight here, but I did it for you guys. Enjoy it. Practice it. Get good at it. Practice it multiple times, okay? It's one thing listening to me and going through it once. It's another thing doing it by yourself. Print off a student copy that's blank. Practice multiple times and get good. You've got 4 more days before the exam. Don't practice the night before. Practice each day about an hour a day. Put in about 4 or 5 hours total or more, depending on you, and then master the problems. And if you can do this set, you'll be ready for the test. See you then.